Okay, so now we're moving on to the last section in this chapter. This section is probably one of the most important out of this chapter because you're going to see the same stuff again when we hit chapter 19. So you really need to make sure you understand this section before you move on to chapter 19. So we're going to talk about cardiac output. And cardiac output is related to both stroke volume and the heart rate. Definition wise, what is cardiac output? It's the amount of blood pumped out by each ventricle in 1 minute. So not both ventricles, each of the ventricles in 1 minute. When we talk about stroke volume, that is how much. So the volume of blood pumped out by one ventricle with each beat. And the stroke volume correlates with the force of contraction. So the stronger the force of contraction, the higher the stroke volume. So the stronger we can contract it, the more we can push out. So it would increase our stroke volume. At rest, first let me back up a second. Cardiac output is equal to our heart rate times our stroke volume. That's going to tell us if we take how many beats per minute that we are having or occurring, and we times it by the amount of blood that each ventricle is pumping out, so our stroke volume, that's going to tell us the amount of blood pumped out by each ventricle per minute, right? So that cardiac output is equal to heart rate times stroke volume. So if we're at rest and our SA node is spontaneously depolarizing about 75 times per minute, then our heart rate would be 75 times per minute. If we're at rest, we're pumping out of each ventricle about 70 milliliters per beat. So our cardiac output at rest is equal to 75 times 70, which is about 5.25 liters, because that was going to be in milliliters, and then you got to change it to liters. So our normal adult blood volume in our entire body is 5 liters. So we actually circulate our entire blood supply through our heart each minute, if not more. Also, I just want to point out, because you're looking at an equation, yes, you need to know it, but also be able to kind of understand if something's directly proportional or inversely proportional to each other. So if we increase our heart rate, we've increased our stroke volume. If we increase our heart rate, we've increased our cardiac output. If we increase our stroke volume, we increase our cardiac output. So they're directly proportional to each other. So our maximal cardiac output is about 4 to 5 times the resting cardiac output in non-athletic people. So about 20 to 25 liters per minute. Maximal cardiac output can reach up to like 35 liters per minute if you're a trained athlete. We have something called the cardiac reserve, and the cardiac reserve is the difference between our resting cardiac output and our personal maximal cardiac output. So if we're talking about cardiac output changes, whether it's increases or decreases, that's going to happen accordingly if either our stroke volume or our heart rate is changed. A couple of things can affect our cardiac output. So if we change our cardiac output, we can also have differences in regulation of our stroke volume and regulation of our heart rates. Okay, mathematically, so we said cardiac output is equal to heart rate times stroke volume. Stroke volume, if we think about it, is equal to our end diastolic volume minus our end systolic volume. Now, if you remember what these were from the previous section, our end diastolic volume was the max amount of blood that we had in our ventricle. So we got 80% just from filling from our atria, dripping into our ventricles. Then our atria contract, and they push the remainder 20% from the atria into the ventricles, and now theoretically we're at 100% maximum in our ventricles. So the 100% max in our ventricles is our end diastolic volume, or the end of the resting phase, because the whole purpose of the resting phase is for us to fill. So end diastolic volume is our max volume that we had in our ventricles, minus our end systolic volume. So our end systolic volume is at the end of systole, so after contraction. And if you remember me saying, when our ventricles contract, they never push 100% of the blood that was in the ventricle out into the aorta or the pulmonary trunk. Some blood always remains. So if we take the max volume minus the volume that remains after we contract our ventricles, that gives us our stroke volume. How much did we actually push out of our ventricle? So if we take our original cardiac output formula, which is cardiac output equals heart rate times stroke volume, now we can even be more specific about our stroke volume and say cardiac output is equal to heart rate times end diastolic volume minus end systolic volume, because this represents the stroke volume. Okay, so again, your goal here is not necessarily to do a bunch of math or equations, but understand the relationships and what's going on. A couple things can affect how much stroke volume we have. One of them is preload. We're going to talk about all of these. Contractility, and then we also have afterload. So preload is the degree to which cardiac muscle cells are stretched. How much stretch are we allowing in these cells just before they contract? So changes in the preload causes changes in the stroke volume, and it's also going to affect the end diastolic volume. And the relationship between the preload and the stroke volume is called the Frank-Starling law of the heart. So if you think, hey, if we don't have a lot of preload, that means we do not have a lot of stretch in our cardiac muscle cells. If we don't have a lot of stretch in our cardiac muscle cells, that means our ventricles can't stretch as much and they can't hold as much volume. So that's why it affects the end diastolic volume, because that's the max volume. It wouldn't affect the end systolic volume because that's after our ventricles contract, and all we have left in there is the remainder blood. It doesn't matter how stretchy our ventricles are or the preload, because we only have a little bit amount of blood. The only time the stretch or degree of stretch is going to matter, or the preload, is when we have the max amount of blood, which is the end diastolic volume. And again, like I said, this relationship between preload and stroke volume is called the Frank-Starling law of the heart. We also have cardiac muscle exhibits a length tension relationship. So at rest, our cardiac muscle cells are shorter than optimal length, and this is also going to lead to dramatic increase in contract